So I would like to talk a little bit about entropy, information, and compression. So the key question is, how do we measure information and what is entropy? And I'll have a simple example of, let's say, raining in Seattle. So we'll come up with a simple toy model. And let's say every day we flip a coin. And let's say it rains with 80% probability independently every day, let's say in Seattle. So in 100 days, we observe a sequence of, let's say, rain, rain, not rain, rain, not rain, and so on for 100 days. That's 100 bits. And the central issue is, how much information is there really in this sequence? And you can ask me, well, it's not 100 bits. It's actually less than that. And that's the shocking thing I'm trying to tell you. A related question to that is, this sequence, is it possible to actually compress the sequence of 100 outcomes of rain, not rain, and maybe represent it with fewer than 100 bits? So the Shannon's compression theorem, the central thing I want to talk about, is that in order to compute this, we have to compute the entropy of this variable that becomes 1, let's say with probability 80%. And after we compute the entropy, then entropy is the ultimate limit to compression for any sequence. In 1948, Claude Shannon wrote his landmark paper that single-handedly defined what is information, what is entropy, proved his compression theorem that we're talking about today, that entropy is the limit of compression, and also found the limits of reliable communication in the presence of noise, which is another story. Now, to understand compression, it's easiest to understand it as a game between two people. Now, in this game, we have two people, Alan and Claude, and they meet before this compression starts, and they know the statistics of raining in Seattle, but they do not know the actual realization of how this random variable realizes. So they will agree in some complicated compression scheme. Let's say they say, if I see 1, 1, 1, 1, I will send you 0, 1, otherwise I will send you some other complex patterns that they can agree, some compression code that they will use. And then the way the game works is, Alan will go to Seattle, and he will observe the actual realization, the actual sequence of 100 days, let's say rain, rain, not rain, and so on. And then he will send some bits, some compressed bits to Claude based on the scheme that they agreed upon. And now Claude receives this sequence, and he has to use that sequence and the scheme, but no other information, to decompress the sequence and produce this sequence here. And we will say that this compression scheme was successful if the reconstructed sequence here agrees with the original sequence. And you may be thinking that it's actually impossible to represent any sequence with 100 bits by compressing it in fewer than 100 bits, and that's correct. But if you allow a little bit of probability of error, and that's part of the genius of Claude Shannon's setup, then if you allow arbitrarily small probability of error, as the number of days goes to infinity, you can actually compress these sequences. So the first thing to realize is, let's say that it always rains in Seattle. There is actually 0 information in this sequence, which means this sequence is compressible to 0 bits. And this is because Alan and Claude, when they meet before the game starts, they know that it always rains in Seattle. So they say, you know what, Alan is not going to send anything. And then Claude will just print 100 once, and he will be correct, and therefore we can compress deterministic sequences with 0 amount of information. Generally, entropy is the limit to compressing any sequence, and there's a magical formula that Shannon proposed, that for binary variables that take only 1 and 0, let's say they take the value 1 with probability p, this is the formula for the entropy. So it's minus p log p plus 1 minus p log 1 minus p. And the base of the logarithm here is base 2, as I say here, and by continuity we always assume 0 log 0 is 0. Now, if you plug p equals 0 into this formula, which is the entropy of the variable that never rains, you find, doing this little calculation, that it's actually 0 bits. So if it never rains, as we said before, there is no information. It's perfectly compressible. Similarly, if it always rains, if you plug in again p equals 1 into this formula, you're going to find that again it's 0 bits. So again, it's a perfectly compressible sequence, which means no information. But let's say it rains 80% of the time. If you actually calculate this, you're going to find that it's 0.721 blah 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 bits per day. Okay? And Shannon's compression theorem is now saying that we can actually compress 100 bits of rain data into approximately 73 bits of compressed information that Alan will send to Claude, and then Claude will, with high probability, be able to reconstruct these 100 bits of rain data. Now, if it rains more, let's say it rains 90% of the time, then if you calculate, just plugging into this formula again and using a calculator that has logarithms, you will find that the entropy is 0.46 bits per day. So you can actually compress 100 bits of information with less compressed bits, now 47 bits. So there's less surprise when it rains 90% of the time, which means there's less information, which means there's more compression. If it rains 99% of the time, then this is even further compressible. And if it rains 999% of the time, then this becomes basically zero, as it always rains or if it never rains. Another thing you can observe just by plotting this binary entropy formula is that the only case where you will get a 1 is when P is exactly half, which is a fair coin, which means that every time nature flips a fair coin, so we have maximum surprise, which also says that we actually know nothing about rain versus not rain every day. And that's these sequences that we call incompressible. So if you have a fair coin, 50-50, then you have 1 bit per realization, which means you cannot compress it at all. Now, I want to give a little bit of intuition about this compression theorem. There are 2 facts we need. The first one is pretty straightforward. To describe one object from a list of L things, I need log L bits. For example, let's say that we have 4 objects like banana, orange, apple, and mango. Claude and Shannon can sit down and say, you know what, I'm going to represent banana with 0, 0, orange with 0, 1, apple with 1, 0, mango with 1, 1. We agree on this. Now, the second fact, which is the most important one, is when you're compressing these random sequences that are independent realizations of a random variable, you don't need to represent all the sequences. There's actually very few sequences you actually need to represent. Because only those sequences will appear with very high probability, and the rest of the sequences you can ignore, and then you're not going to fail with very high probability. So these sequences that do appear, we call them typical sequences. And therefore, by fact 1, we only need logarithm of the number of typical sequences. This is the number of bits we need to compress, and then we will succeed with high probability. Now, to understand this a little better, when I have a coin, let's say that is, I flip it 100 times, and it comes heads with probability 0.1, I expect to see about 10 heads in 100 flips, right? So Alan and Claude will only worry about representing those sequences with, let's say, exactly 10 heads. So if it rains fewer or more than 10 times in 100 days, they will just declare failure. So if it's not a typical sequence, they will say, I'm not going to represent that. So let's say they were only representing those sequences that get exactly 10 sunny days or exactly 90 rainy days in 100 positions. How many ways are there to place 10 things in 100 positions? Well, from combinations, you may remember this is 100 choose 10. And therefore, the number of bits they need to send is basically logarithm of 100 choose 10. And if you calculate this, it turns out to be approximately 47 bits, which is exactly the number we had before for a 90% rain situation. So where this came from is not a coincidence, and that's the whole magical thing, is that n choose k, the formula for combinations, has this complicated expression n factorial over k factorial times n minus k factorial. But using Stirling's formula, you can get to this simplification, and magically the entropy function appears here. So k over n is the fraction of days where it rains. So this log L here is exactly 100, the number of days, times the entropy, the binary entropy function for P. And this is always true just by Stirling, really. So this is really the key things you need to understand, that we only need logarithm of the number of typical sequences to compress and succeed with high probability. The magical thing that Shannon used is that sequences for any random variable always become uniform over the typical set, and that this set has size equal to the entropy of the random variable. This phenomenon is called the concentration of measure in probability, and the simplest version is the law of large numbers that you may have seen in a statistics or probability class.